Today we are going to learn how to design fuzzyLogic controller by making use of fuzzyLogic controller design app. And what we are going to do is that I will first of all give overview of fuzzyLogic controller. Thereafter, I will present our problem, which I will analyze. After the analysis, I will take the class to fuzzyLogic controller app in MATLAB environment, so that everything that I will discuss will be demonstrated in that particular environment. That is what we are going to do. My name is Sunday Aditono of Department of Electrical and Electronics Engineering, University of Lagos. The figure that you are seeing on our screen here is presenting the components or the blocks that we have inside fuzzyLogic controller. Actually, I've discussed this particular diagram when I was presenting fuzzyLogic controller to the class. Notwithstanding, for the sake of completing this particular lecture, there is need for us to give overview of what I've done in that particular class. Here, we have inside fuzzyLogic controller the following components: fuzzifier, inference engine, the fuzzifier, and a block that houses rules guiding the fuzzy, or the rules that inference engine makes use of, so as to be able to give a logic output. From this particular diagram, it is evident from the diagram that inference engine happens to be the brain of fuzzyLogic controller. This particular brain that we are talking about will receive fuzzy value from fuzzifier, and based on the rule that has been embedded in this particular box, inference engine come out with a logic expression which is in form of fuzzy value for the decifier to make use of that. Then, what is now the function of fuzzifier? The fuzzyLogic controller understands a language or a value or process a value that is referred to as a fuzzy value. But the desired response here is not a fuzzy value. It is a Krebs value, or better still, we call it a physical value. Therefore, for inference engine to be able to get fuzzy value that it understands, falsifier will take physical value and convert it to fuzzy value. Inside falsifier here, we have what we call membership functions. Membership functions that we are going to have here happens to be a function of number of input variables that happens to be physical values that we are receiving here. Immediately, the fuzzy value is available here. Inference engine will capture it, and based on the rules, inference engine will work on fuzzy value made available or makes available by falsifier, then come out with the fuzzy value output. That particular fuzzy value output indicates what is happening here. But now, based on the rule, then our response is produced. But this particular response that is produced here is a fuzzy value or aggregated fuzzy value. And the output here, the actual output should be physical value. But what we are having here happens to be fuzzy value. For us to be able to get physical value here that is going to work on a system or a plant, then fuzzy value needs to be converted back to the Krebs value. Therefore, we can now try to say that the falsifier happens to be a device or a unit that converts aggregated fuzzy value to physical value that will work on the plant, so as to make sure that output of the plant is more or less equal to the desired physical value here. We call it desired response, and we call the output of the output of a plant as actual response. For us to be able to get for the user to be able to get the desired response here, under normal circumstances, the Krebs value that we obtain here will work on the plant, and the actual response that we are going to get will now be approximately equal to the desired response. That is what a fuzzy logic controller stands for, or that is how the fuzzy logic controller works. Now, then for us to be able to convert physical value to fuzzy value, we need to understand the components or how the falsifier is working. And for the inference to be able to do the needful, there is need for us to develop, some rules that are going to guide inference engine in making a decision that is going to be available to the falsifier. So how are we now going to convert physical value to fuzzy value? I'm going to demonstrate that one in MATLAB environment. how are we going to embed our rules here? I'm going to demonstrate that one in MATLAB environment. And how are we going to diffusify the physical value here so as to be able to get physical value here? I'm going to demonstrate that one too in a MATLAB environment. But before I go for demonstration, there is need for us to present a problem. And that is what I'm going to present now. And after I might have presented the problem, there is need for us to analyze the problem so that by the time we get to the Fuzzy Logic Designer app environment, we know what to do. Then, what's the problem are we presenting? But before I go to the problem, there is need to tell us that instead of having CISO, Fuzzy Logic Controller may be MIMO, and may be MISO, and may be SIMO. That is, MIMO means, or MIMO, SIMO, MISO. MIMO means multiple input, multiple output. We can have multiple input here, and we can have multiple output here. We may have a single output, single input here, and a single output here, and that is what we are having here. That is SISO. And we may have single input here, multiple output here, and that is what we call SIMO, and vice versa. So let us now look at a problem that we are going to use to explain. Then by the time we get to MATLAB environment, I will use that particular problem to demonstrate development of Fuzzy Logic Controller. This is our problem. We are making use of this particular problem as a case study. We are going to analyze the problem here, and when we get to the MATLAB environment, specifically when we get to the Fuzzy Logic Designer app environment, we are going to implement this particular problem there. The problem reads: you are tasked with designing a Fuzzy Logic controller for an air conditioning system that adjusts cooling power based on room temperature and humidity. The goal is to maintain a comfortable cooling environment where the air conditioning system is placed. From this problem, it is evident that the output variable is what we call cooling power. Then the input variable are room temperature and room humidity. Two input, one output. Then we are having MISO, multiple input, single output. Then the next thing to be done is that we need more information from room temperature, room humidity, and from the output variable cooling power. What is the range? And what are going to be our linguistic descriptor? And what is going to be our linguistic descriptor for the humidity? So what is going to be Fuzzy set or linguistic descriptor for the cooling power? That is what we are going to capture in that particular environment where we want this particular AC to be capturing these two input variables and produce this one output variable. To do that, we have been able to come up with some parameters. For the first input variable, which happens to be temperature, temperature is measured in degrees centigrade, and the range of interest is from 10 degrees centigrade to 40 degrees centigrade. And I've been able to come up with a three linguistic descriptor, which we called fuzzy set. That is, one of the parameters here, one of the descriptor here is a cold. The second one is warm. Then the third one is hot. Now, for us to be able to fuzzify the temperature to fuzzy value, then we need membership function. And here, when I was teaching the class on fuzzification using fuzzifier, I told the class that we need membership function. That is, we need to map, this is temperature axis, which is giving us physical value. We need to map it. We need to map it to give us a fuzzy value, which we call degree of membership. And to do that, we need membership function. And we have different types of membership function, or the chip that we can use. We can use triangular membership function, that is a triangular chip. We can use what we are having here, that is trapezoidal shape. Apart from this, we can make use of Gaussian shape. We can make use of Gaussian shape, that is the shape that resembles bell. The shape that resembles a bell, normal distribution curve. So that is what we call Gaussian shape. Apart from that, we can make use of sigmoid. Sigmoid, based on the pronunciation, the shape that assumes x, the shape of x. But here we are making use of trapezoidal shape to represent cold, to represent warm, and the third one to represent hot. And one thing I need to tell you before I move to another input variable is that a given trapezoidal shape requires 4 coordinate system to represent it. For instance here, we are having one coordinate system here, second coordinate system here, third coordinate system here, and the fourth coordinate system here. Then for this point in mathematics, the coordinate point here, since this one is 15, is going to be 15, is 0. This point is going to be 25, 1. This point is going to be 30, 1. This point is going to be coordinate system that can be described as 36, 1. Therefore, better in fuzzy logic controller arena, we don't need to specify degree of membership, when indicating coordinate system, because by the time you mention those 4 points, the system has known that this one is 16, 0. This particular point is 25, 1. This point is 30, 1, and this point is 35, 1. What you just need to mention, because we are interested in converting physical value that we are having here to fuzzy value here, Therefore, what you just have to indicate happens to be the physical values. That is, the first point is going to be 15, 25, 35, 30 rather, and 35. Now, I'm now starting from this. Then when you count the number of points that we have here, we have 1, 2, 3. Therefore, we know the coordinate system here, which is 15. We know the one here 20, but we know this one here 10. In order to make it 4, you are now going to specify 10, 15, 10, 10 again, making 2, 15, making 3, and 20, making 4 points. The same thing here, we are having 3 points. Therefore, the point here is for the first point, 30, 35, 40, and 40, making 4. And the same thing we are going to do for the humidity. Before I go to the humidity, temperature here, the range is from 10 degree to 40 degree. And when you are drawing your membership function, you should try as much as possible that the second membership function should overlap the first membership function at a given point. This is where the fuzzy is coming from. That is, in this particular area, we have cold, we have warm. So then we are now going to make decision. The inference system is going to make decision pertaining to this point based on the law or rules that we are going to supply. That if something happened, what is going to happen? So the same thing here, there is need for the overlapping at a certain point. And one thing we can do is that when you draw your membership function, you make the data that you have been able to capture from the environment where the system that fuzzyLogic controller is going to work with is going to you capture the information so as to be able to get the correct scenario here. So for the humidity, the range is from 20, the physical value range is from 20% to 90%, and you can see 20 to 90. And for us to be able to describe what is happening when we are considering humidity, then we have come up with 3 linguistic descriptor too. Dry, is humidity is the environment in time of humidity. Is it dry? Is it comfortable? Is it humid? Then we use trapezoidal shape to represent dry, to represent comfortable, and to represent humid. And the same thing that I did here, I did it here too. We need 4 points. To represent this particular point, we need 4 different coordinate systems. The point here is going to be 20, 20. This point is going to be 40 and 60. 20, 20, 40, 60, giving us 4 points. Then we start comfortable in between. We make comfortable MF multiple MF to be membership function to overlap at this particular area. We start by from 40, 40, or 60, 50, 70, 80. This the last membership function that's representing humid, we start from 70, 80, 90, making 4 points. And by the time we specify all those things in MATLAB environment, the membership function, the degree of membership versus physical value for the temperature, degree of membership versus percentage of humidity will be represented. The fuzzyLogic controller will try to come up with this. So that is what we need to specify happens to be the coordinate systems for cold, for warm, for hot. Then the system is going to draw this thing itself. The same thing here, you specify. As we have defined, for the input variable, so we are going to define the same thing for the output variable. What am I trying to say? What we have been doing here, we have been able to carry it out, or we have been able to, by the time we supply necessary information about the coordinate system for this, coordinate system for this, coordinate system for this, and we try to customize the input as temperature, then the fuzzy inference system will come up with this particular membership function itself. The same thing with this one. Therefore, that in doing this, we have been able to develop that particular block that we call fuzzifier block. That is, what we are doing here is what we call fuzzification. That is, fuzzification can now be defined as a process of converting physical value to fuzzy values, so that in the so that inference engine will be able to make use of that particular value together with the rules that we are going to develop later, so as to be able to come up with a fuzzy logic that we can use to control our plant fire. This is fire, because fuzzy value that we are going to get from inference engine cannot work on the plant, and therefore the fuzzifier will now tries to convert fuzzy value back to the physical value. Physical value that we are now obtained will now work on the plant, so as to be able to make sure that necessary parameters that we expect from the plant we will be able to achieve them. Now, this is output variable, and the name for the output variable is cooling power, and it ranges from 0% to 100% to 100%. And for me to be able to explain how we normally make use of a triangular shape as a membership function, then I'm making use of a triangular shape here. Then here, you see that cooling power is low or medium or high. These are the fuzzy set, which we call linguistic descriptor. We need to describe the cooling power of the environment we are interested in making it to be comfortable. Under normal circumstances, the situation, the condition of the temperature of that particular environment, the humidity will determine whether the area is going to be, the cooling power of the area is going to be low, or it's going to be medium, or it's going to be high. Then, so we make use of a triangular shape to represent that. Here, for you to be able to have a triangular shape, you need 3 good points. The first point is this, which is a coordinate system 1, coordinate system 2, coordinate system 3. Then that is, for instance, here, for us to draw this medium, based on the parameters, based on the range given to us, then by the time we specify is 0, 20, and 40. This particular membership function is going to be produced by the system. Then by the time we get to this particular area, the membership function named or tagged medium will be what we are going to specify to draw a medium membership function is going to be 30, 50, and 70. 3 points. Then for us to be able to specify high membership function, we will specify this particular 3 points, 60, 80, and 100. That is, the first point is indicate, if the thing is 60, the fuzzy value is 0. If the thing is 80, the fuzzy value is 1. Then if the physical value is 100 here, that is far away is 0. So, but when let us believe that we are drawing the 70, when we have 70%, you draw it to this area, the value here, you now sketch to this area is going to be the degree of membership or physical value will now be something like 0.6. So that is, but our own is just to specify that the fuzzy inference system is going to make necessary decision when it receives certain information from the inference system. Now, having done that, for the inference system or inference engine to be able to perform its operation, it needs two important information. The first one is a fuzzy value from the fuzzifier. Then the rules that are going to be supplied by the rule-based block. And for here, I have been able to develop three rules. The first rule is goes like this, and I've told the class that in development of fuzzy rules, we use if-then statement, and I told the class that the statement in between if and then, they are referred to as antecedents, and anything after then, that is the decision that is going the inference engine is going to come up with is what we call consequence. The consequence happens to be the product of antecedents. So here, one thing you need to look at here happens to be the logic that you use to combine the two antecedents here. If temperature is cold and it's very, very important, and humidity is dry, then what is the consequence? The consequence is that cooling power should be made low. Now, what are we trying to say? What we are going to examine here is and. That is, what we are saying here is that if temperature is cold, that and we assign with 1 to it, that one is going to be 1. If humidity is dry, then the weight, that one is going to assume 1. Then the cooling power is going to be low because we are making use of and. Knowing fully well that we are trying to say that 1 this time around is true, 0 is false. So 1 and 1 in Boolean algebra will give you 1. And this time around 1 is cooling power is low. But let us assume that humidity is not dry, but is humid, meaning that this one is 0. Let us assume that temperature is cold, that is 1. 1 and is 0, because this one is false, we give false. Knowing fully well that 1 and 0 is 0. So that is that. And for the system to be able to understand that, then there is need for you to make use of your hand. And when we are setting our fuzzy inference system, we are going to state, we are going to define, we are going to declare that when we are making use of and rule, the output that we are going to obtain should be minimum. And the same thing here, but the antecedent here, they are different from the first rule. The temperature is warm and humidity is comfortable. Then we still use and. For us to be able to make cooling power, which happens to be the consequence, to be medium. Then temperature is warm, should be 1. Humidity is comfortable, should be 1 for you to have power to be medium. But any attempt for one of these particular antecedents, to be false, this one is going to be false. But for us to be able to understand what I'm trying to say, I made use of or here, or, and here we use or. Or is either here or there. That is, if this one is 1, if temperature is hot, that is 1. Humidity is humid, that is 1. 1 or 1 is 1. Then the cooling power is going to be high. But if temperature is hot, which is 1, humidity is comfortable, that is 0. With all here, the cooling power is still going to be high. The cooling power is still going to be within the range of high. But if this particular area happens to be the first, if this one is correct, humidity is humid, but temperature is cold. Hot, just because of hot, we are still going to have high. The condition that's going to make cooling power not to be high is when this particular one is false and this one is false. But these are the rules. That is, I'm going to show you how to build your fuzzy rule block. And when you now do that, then we have done what we want to do, because we have been able to develop fusifier by way of adding input MF. We have been able to come up with a fusifier by building what we call output variable. We have been able to develop rule-based flow block by loading what we have here. Then we are now we have been able to customize our system, which is fuzzy inference system, by saying that when you are making use of and or the result that you are going to use, the output must be minimum. When you are making use of or, the output must obey maximum. And for us to be able to diffusify, we are going to make use of we have many approaches, but the most common approach happens to be the usage of centroid, center of gravity. That is, what we are trying to say is that in mechanical engineering class, you can determine the center of a given object that happens to if the object contains many shapes that are aggregated together. We find the area of each of the areas that form the object under consideration, and we are now going to divide the sum of the area all over the sum of the length from a certain point to another point. If you are interested in determining x mean, you determine it by making use of the centroid, that you capture how far each area is far from the origin. And when you want to determine y bar, which is y mean, you determine the area and you divide it by the the length, how the length is far away from the center of that particular object. And that is why we normally make use of centroid. But apart from making use of centroid, we can still make use of other shape. One example is by making use of what we call MOM. What is MOM? The MOM is abbreviation for the mean of a mass. If you determine the weight of a given object, you now determine their mean. We can still make use of that particular approach. We can make use of another approach entirely by sector, and so on and so forth. But the most commonly used technique or method for the diffusification is what we call centroid, and that is what we are going to use here. Then Afun tries to explain how we can build our rule-based block, how we can build our diffusification block, which we call diffusifier, and how we can build our fusification block, which we call fusifier. We can now go to the MATLAB environment to demonstrate this particular problem, to demonstrate how we can realize this problem in fuzzy logic Designer app environment in the MATLAB environment, and we now go to fuzzyLogicDesigner app environment immediately. I'm taking the class to the MATLAB environment where we are going to demonstrate what I've just discussed now. So I'm taking the class there immediately. I'm taking you to the MATLAB environment where you are going to see, where we are going to demonstrate. And this is my MATLAB environment. We are now in MATLAB environment. That is, I've launched my MATLAB environment. And how do we get to fuzzyLogic control designer? So fuzzyLogic designer, then two ways. It's either you type fuzzyLogic designer here and you click enter, you are going to get to that area. That is, you say fuzzy. I'm typing. Then logic, you need to write logic in capital letter. You start logic designer. That is one way of getting to the app. Another way is just to, where you see my cursor now. You click on app, then we go to the control system design and analysis, because it's under control design and analysis. Then this is control system design analysis, and we have different app there, and this is where we are going. That is fuzzyLogic designer. That is, the version that I have here is fuzzyLogic Toolbox 24.2, because the version of MATLAB that I'm using is 2024 version. So design and test, that particular app is used to design and test fuzzy inference system before we program our hardware, that we are now going to connect to a plant. So that, when you click on this, you are going to the environment. But in my own case, I want us to enter through this area. And for you to enter through this area, what you are going to do is that you enter. When you enter, you wait. And by the time I enter, automatically what you are seeing here as ready, we turn to busy, be busy, meaning that that the thing is now loading fuzzyLogic designer app. I'm entering it, so I'm now entering it. I've entered. I want the MATLAB to go and search for that app. Then you see this particular area that is ready before is now busy. So I'm now waiting for that particular app to be loaded. Then we are going to start from that particular area. I'm waiting. So by the time the thing is available, I'm going to continue. I want to make it real, and that is why I've not loaded it before now. So the thing is now loading. Then let us wait until the thing is now available. Thank you. Yes, you can see that it has started loading, and it will soon loaded. It has started loading. It has started loading. Here we are. It's still loading. It's still loading. So yes, this is it. So this is we are now getting to that particular area gradually. Then I've told the class that under normal circumstances for fuzzyLogic designer, we can either go for the Mandani or Sugano. And I told the class the difference between the Mandani and Sugano. And I've told the class that we go for the Mandani. Therefore, we go for the Mandani, we take this template, I've clicked on that, and the thing is now going to open. I'm waiting for it. I'm waiting for, yes, this is a fuzzy inference system environment, and this is where we are. So that is this Mandani 1, and that is that, and the information and Mandani 1 are here. And one of those things that you need to do when I was discussing the problem with you is that we now tries to name our fuzzy inference system. We customize instead of calling it Mandani type 1, which is here. You know, I'm talking about the right side of this particular, the far right away. We call it right, right, this particular right side. Then instead of calling it Mandani type 1, you click on that and we change the name. We change the name, we customize it to our taste. Now, then since we are interested in controlling temperature, I'm going to name it temperature, temp, temp, temperature, 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 coming. We are going to name it temperature control, control. Then for me to be able, because I've been able to have one control system, one temperature control before now. Let me call it control 2. Control 2. Then all these property that we have here. So I've told you about the AND method. When you have when you hand two variables, then when one of the variables happens to be minimum, the output is going to be minimum. We retain it like that is correct. When you are holding two variables, then if one of the variable is minimum and one is a maximum, the maximum is going to be returned. The maximum is going to be returned. And in a situation whereby you are having two membership function, and you try as much as possible to hand them this one membership function here, and another one we said, and therefore the result that you are going to obtain will be minimum. And by the time we are interested in falsification, if we are interested in falsification, then the falsification, when is normally take maximum, because it's either this or this. Because by the time you get to two things, you say, am I going to take this or this? So then we are going to make use of maximum. Then the falsification method, I've told you that we have different type of the falsification method. For us to be able to convert falsify obtainable or obtained from inference engine back to the physical value that can work on the system. For instance, here we are working on an AC system. So for a system to be controlled so as to be able to determine the level of cooling power in that particular environment where it is placed, there is need for us to take a method that's going to do that one for us. Here I've told you we have centroid, we have bisector, we have MOM, and we have sigmoid. This is a sigmoid. So this MOM is a mean of mass, but the most popular there is centroid. Then that is fine. Then we have been able to customize our fuzzy inference system. You see the name has changed to temperature control 2. Then this is the name of a fuzzy inference system. And here we are having, according to the information about fuzzy inference system that we have 2 input, 1 output, and 9 rules. But just let us forget about that. We are going to customize it to our taste. Let us believe that instead of 2 inputs that we have here, let us believe that we need additional 1 input. You come to this area, so this is what we call tuning. You tune this thing to your taste. Then when you click on this, an additional input is going to be added to this particular area, but we need only 2 inputs. Let me click on it and see what is going to be the result. So I click on that. We are going to have additional 1 input, making 3 input and 1 output. If you want to increase, this is third input. So but here we are not interested in 3. We are interested in 2 inputs. Therefore I'm going to do away with this. So then I will delete it. So I've deleted that. I've deleted input 3. Then we are now going to work on what we call input. Then I'm now on input. Then I need to customize this my input. So this is here. You come to the right hand side of this particular plane and customize. Here we are having input 1, and our input 1 here is temperature. So you change the name to temperature. You are now developing, that is development of our system. That is development of our system. So let me just see. Yes, you change these ones to temperature. That is temperature. Yes, that is temperature. Then the second one is humidity. That is we are developing humidity. Yes, humidity. Then we need to change the range of the environment where we find ourselves. Let me find the range so that I will put appropriate range there so that we don't mess up. So the range that we discuss in the class happens to be, I'm looking for it. Yes. Yeah. So this is the range. The range is from for the temperature is from 10 degrees centigrade, 10 degrees centigrade to 40 degrees centigrade, 40 degrees centigrade. Then whereas for the humidity, the range is from let me see, 20. The range is from 20% to 90%. Now I need to add one more thing before I leave. We have 3 linguistic descriptor for the temperature. That is why we are going to let it fly. We have 3 for the humidity, but let us believe that we have 4. We just change that particular value to 4. So having done that, we can now come to temperature and customize it to our taste. And you can see that temperature has opened here, and we can now customize them to our taste. So here, the first membership function, from our discussion before now, it is we call it code. That is code. Then I need to customize code to my taste. Then the second membership function is known as the worm. So this is my worm. Then the third membership function is a hot. So you change hot. Then the next thing that's going to follow is that what type of shape are we using for it? See, we have different shapes. Say we have different sigmoid, Gaussian, general bell. That is what I call general bell, which is a sigmoid. Then linear general bell, which is S shape, Z shape, pi shape. I think you can make use of, but here we are making use of a trapezoidal shape, and this is trapezoidal shape for the first one. Then here I'm taking trapezoidal shape for the second membership function there, and I'm taking trapezoidal shape for the third. Then the range that I've told you, which is what I call coordinate point. Then for the code, I've told you that for the code is going to be 10 10 10 10 10, in order to make sure that we have 4 points. So you open a bracket, triangular bracket, then 10 again. We have 15, third point, and for the last point, then we have 20. To be able to describe that 20, then I close that. That one has been done. Then you will see that the thing has appeared in blue color here. For the middle membership function, which is going to assume trapezoidal shape too. I'm starting, in order for the middle trapezoidal shape to have to overlap the first trapezoidal shape at certain area. I start from 15, then move to 25, then we get to 30, and the last point is 35. 35 I now close. It is closed already. Then for the hot membership function, for it to be able to overlap the second membership function, which happens to be warm, a certain area. I'm starting from 30, then 35, then the last range is 40, but we need 4 points to model the trapezoidal shape. I put that there, and that is completion of that. Then you can see that temperature had changed, has assumed the value that we want. And for you to see it clearly, you can come to the membership function editor. Here, if you don't have the shape that you want, you can change it a little bit, so that let's believe that we want the thing to come to this area. You can come to this side and put it here, so as to be able to get what we want. Now that is that. So we have done something for the membership function. We are now going to the humidity. This is humidity. Then humidity has been highlighted. Then we are going to change this particular value to our default. That is, we have 3 linguists stored here for it. Dry is number 1. Then comfortable is number 2. Comfortable. Then the third one is humid. Then humid. Then we are still maintaining trapezoidal shape. the trapezoidal shape is going to be taken here. We are taking trapezoidal shape here. Instead of triangular is default. Trapezoidal shape here. Then on coming to this side, then we are going to specify the range of dry membership function. And when I was discussing, I told you I'm taking 20, my 30, the last point is 60. So that is that. Then here I'm taking for the medium, for the comfortable membership function, for it to be able to overlap the first membership function somewhere not far away. I'm taking 40, which is in between 30 and 60. Then the second point there, I'm taking 50. Then the third point, I'm taking 70. And the last point, I'm taking 80. So here, I'm taking for the last point, umid. Then for it to be able to overlap second membership function, I'm starting from 70. Then I'm getting to 80. 80. Then the last point is 90. But we need 4 points to describe a trapezoidal shape. I'm ending it like this. So that is that for that. Then you can see that the thing is now complete. For me to fill it, I will come to this area to see what I've done. You see, this is it here. So having done that, we can now go to the fuzzy inference system again. Then go to the output. This is my output, which I have not been able to, no, it has not been customized. And here my output is cooling power, cooling power. So cooling power, I've done that. Then what is the range? The range is from I think from 0 to 100%. Yes. Then we need 3 membership function there too. So then that is that. Then for me to be able to do that, I need to highlight cooling power. It has been highlighted and it's now loading. So we need to specify the range for the first membership function, which we have given it a name that are low, medium, and the last one is high. So high, high. Then I've told you we are making use of triangular shape, and therefore using triangular shape we need 3 parameters for us to be able to describe the membership function low. And here the 3 points are 0, 3 point is 20, and the last point is 40. Then I close that. Then here I'm having the medium. Here we are having 30. We are having 30. Then the peak point is at 50. And the third point to describe medium membership function is 70. Then for high, in order for the large triangular function to overlap the second membership function, what I'm going to do is just to start in between 50 and 70. Then I'm starting with 60. Then highest point is going to be at 80. and the last one is going to be 100, and therefore we have now been able to do that of cooling power. We use triangle. The first point is 0, 20, 40. The third membership function is 30, 50, 70. Then the last one is 60. Then let us fill it. So membership function for that. No, yes, we need to come back to this area. I've not been able to. This one's supposed to be 100. So the thing is not going to give us what we want now. Can you see it now? So that is why it's good for you to fill before you just make as on the range from 0 to 100. So we go back to this area. Then the next thing to be done is just to come up with rule that fuzzy inference engine will work on when it receives this is our fuzzy inference system that we call it a temperature control tool. So it needs fuzzy inference, the block, the rules are built here, and this is the rule. You come to the rule, then you need to work on it, and we now wait. So we have 9 rules. Then it has to be edited. So you come to the rule editor. Then this is rule editor. You are now going to be taking the rule one after the other. So the first rule is this. So the first rule is what we are having here. We are now waiting for it to load. So rule 1, rule 1. Then under normal circumstance, we now try to look at the rule. So it has now come up. Our rule 1 here. This is what I'm trying to tell you. That is, this is our rule 1. Then we assign weight 1 to each of those components in that rule. That is, temperature is going to be 1, humidity is going to be 1, cooling power load 1. So here we are having temperature is cold. I'm going to the rule. So temperature is cold, correct. Then you go back to the connection and connect temperature to humidity, but humidity is dry, correct. Then what is going to be the consequence? Cooling power is going to be low, correct. So we are okay with that particular rule, so we don't do anything with it. So we leave it the way the thing is. Then we are going to the rule 2. Is rule 2 in line with what we want? So this is rule 2. That is, rule 2 is talking about temperature and humidity, which is the same thing with our own. Temperature is warm, yes. Humidity is and we still make use of connection hand. So but this time around, humidity is not dry, it's cool, it's comfortable here. We pick this comfortable. Then the consequence, cooling power is supposed to be medium, not this is it. This is what we are going to have. So that is what rule 2 is trying to tell us now. We have now been able to come up with rule 2, and that one has been modified. Let me go to this rule. So rule 3 now. Rule 3. Then let me go back to rule 2 and try to see, yes, if temperature is warm, humidity is comfortable, then cooling power is medium. I've gotten that. Yes, that is rule 2. Then let us go to rule 3 and modify rule 3 to our taste. We are now in rule 3. Rule 3 is talking about temperature is hot, yes, but instead of and, we are going to pick or, because that is what we have in our this thing. But humidity is comfortable, not dry. We are going to come to this area. You pick comfortable. We have adjusted to our taste. We have able to adjust it to our taste, and the consequence is going to be cooling power high, not low. Then you pick this one, and you come up with high. So that one has been done. So we have gotten our 3 different rules, but other rules we don't need them. Therefore, they are restricted for you to click on them and be deleting them. So that's going to remain. You are going to have only 3 rows that you need. So the thing is going. Yeah, that one has gone. So that one has gone. Yes. Then we have yes, we need to go do away with this. So we wait. Then you delete it. That one has gone too. So then you come to this area, you click on it and you wait until cancel come up. So delete. I've done that. Then that is the fourth rule. Then we are having another fourth rule. Then we wait. Then you delete it, and that one has gone. Then you come to this one. Oh no, you wait. Then you delete it. That one has gone. Then come to the last one. Then you wait. Then we delete it. So therefore we have been able to load the 3 essential rules that we need to be able to work with our system. Therefore, I'm going back to this particular system. Let me still read our rule again. That is, if temperature is cold, the cooling power is low. Yes. If temperature is humid and uncomfortable, then let me check. Yeah, uncomfortable. The cooling power is medium. Yes. The third rule: if temperature is hot or humidity is comfortable, then oh, I made a mistake. I will go back to yes. Then the rule 2, or humidity is humid. Then we need to work on this. Is that is here is humid. We pick humid. So that is that. It has taken that. We have taken that. Let me confirm again. Yes. Yeah. Is high. Is it high? Yes. Cooling power is high. It's going to be high when temperature is hot and the humidity is humid. High power. Yes. Rule 2. Medium. Humidity comfortable and temperature. Yes. Then rule 1. Fantastic. So we have been able to get to where we are going. I'm now going back to my fuzzy inference system that is named temperature control 2, and we have now been able to build our fuzzy rule block, and we have now been able, here we have inference engine. Our inference engine, fuzzy inference engine, the input that we are going to supply is going to be fuzzified. Fuzzy value is going to enter here. Fuzzy value is going to enter here. Then Mandani is going to fetch the fuzzy rules and tries to use the rule to determine what is going to be the effect of what is obtaining from the two input variable here, two input block. And after doing that, the result that is going to obtain is going to be sent to the fuzzifier, and the fuzzifier is now going to relay the result to be able to drive a plant. Because that one fuzzy value is going to be converted to the physical value, and that one is now going to run the plant. Now, for us to be able to look at what is going to happen, we can see what is happening using 3 different approaches. The first approach is that this is it. We now need to run the system using rule inference system. Then when you click on this, then you can now supply the condition of the environment where the plant is placed. Then that particular condition is, you are going to see the information about it. So this is what we are talking about. So this is it. So here this is our input variable. This is what is coming to the fuzzy controller: 25 degrees centigrade and 55%. 25 degrees centigrade and 55%. Then when temperature is 25 degrees centigrade, this is what we are going to have. That is for the 3 membership function, and for the humidity of 55%, this is what we are going to have. So for the first one, that is humidity, I think cold, dry, then this is going to be the output. And you can see here cooling power is going to be 50. That is what we have here, this and this try to give us this. The second rule, this and this give us this. And the third rule, this or this one is or give us this. You see that here or here. Then what we are now trying to say is that the aggregated value that we are having here, is not going to give us this. And you can see the thing is at middle. At middle, since from here to here is 0, from here to here is 100, middle is going to be 50. The cooling power is going to be 50%. Let us now believe that the temperature has now changed. Let's change the temperature to something like 45 degrees centigrade. The temperature is now changed. It now changed. So under normal circumstances, let us see what is going to be the output. So that is under normal circumstances, you now wait. So for what have you? Let me change this one to 45. Then I'm now returning. No, okay. 45. You take it to 45. So change this was to 45. Let's see. So you are now going to see what is going to happen. So with 45, we can now try to see what is going to happen. That is one way. I'm coming. I see it misbehaving. So let me change these ones to 45. So inference engine 45. So 45. Something is wrong. Oh, the thing is not changing because the maximum temperature that we are having happens to be 40. So let me change it to 35. Fantastic. So if you have something that is higher than the range, the thing will not do anything. 35. So 35, you see, with 35, we are now having 80 cooling power. But let us now believe that this one is now 85%. Let's see what happened. With 85, see, the thing is still 80. So just because of all rule. So let us believe that we now change this one to 65. Let's see what happened. So the environment is now changing. This is what is now going to be the cooling power. So with 65, we still get 80. So let's say with 45%, let's see what happened. So 45%, it has changed. It still 80, and that is one way of trying to see the effect of changing in input variable and the consequence of this particular changing on cooling power. Another thing we can do is by coming to this area using control surface. So control surface, let me just do away with this. So the control surface, you click here, you can still try to see the shape of the surface, how the surface will be, and tries to see when you try to go around the surface, you are going to be seeing the effect on this is the surface. This is our surface that you are going to get. It is presented in what we call three-dimensional plot. That is Z axis is what we call the cooling power, as you can see it here, and this axis here, the y axis happens to be for the temperature, and the x axis happens to be for the humidity. Then by the time you are now moving around this area, you are going to be having effect. You know, you can read what happened when, so that is it. That is when temperature, I think, yeah, temperature is X. When temperature, no, humidity is X. When temperature is 14.2857 degrees centigrade, and humidity is 60%, then cooling power is going to be 50. Let us believe that we move it to another area entirely here. So that is at that particular point, when the temperature at that point, the temperature is 16 degrees centigrade and humidity is 75, the cooling power is going to be 72. That is another way. Another point is that we can still go to the MATLAB environment. We export everything that we have done here to the MATLAB workspace, because this is a fuzzyLogicDesigner app workspace. We are working here. So you come to the tuning through what we call export here. Through export here, let me go back to the fuzzy system. This is my fuzzy system. I'm now trying to export everything that we have done here to let me return this one to the rules. So I'm now going to I'm now trying to, let me see, I'm now moving everything that we have here to what we call so I'm moving it to MATLAB workspace. Then command window is not going to serve as our environment. So you click on this, then you wait. So when you now, let us wait until we get to the command until we get to the MATLAB. We export everything here. Here we are. It's trying to say that, are you interested in exporting? Temperature control, that is the name of fuzzy inference system that we have built. So I export it from here. Then then we now go to the MATLAB environment, and we see how we are going to make use of command window to represent our room where the AC system is placed. And here I'm getting there now. This is the environment, and this is what I'm talking about. The temperature control hyphen 2 is already there, and what we are now going to do is that we are going to make use of a command that I have told the class about, that is ever, FIS, FIS. Then command. Then let us believe that we say cooling power. Cooling power is our output. Hyphen power. Then is equal to, I wanted to evaluate my fuzzy inference system. I will now write FIX. Then I open a bracket, I close the bracket. Then under normal circumstances, I now try to call this FIS, fuzzy inference system, named temperature underscore control underscore 2. That is the name, comma. Then the input, the two input, let us believe that when the temperature is 25 degrees centigrade and humidity is 55 degrees centigrade, then we got 50% cooling power. Let's see what the cooling power is going to be. That is it. Cooling power is equal to 50%. Let us now try to copy this one again, and we try as much as possible to change the input parameters. So the input parameters, I want to change it from 25. Let us believe that we now change it to 35, and we change this one to 75. Then the cooling power Let's see whether the thing is going to change. It's now changed to 80%. And that is the end of my discussion with the class today. And you need to understand one thing. We have done two things. It remains another thing that we will do. Because after you might have finished all these things that we are doing, then you save, you know, the FIS that we have developed, and then you now open it as a M file. You now convert M file to C sharp or C++. Then C++ that you are now been able to obtain, you now program it into an hardware. And when you now do that one, you can now carry the hardware that you have gotten together with a necessary sensor and so together with the necessary sensor and some interface, so that when you connect it to the AC system is not, this particular controller will now be controlling the AC, and you are now going to be getting what we have been able to do. And that is the third step that we are going to do. And that one is going to be an assignment that we are going to build, and we are going to experiment what we have now been able to do, so that we are, the work is going to be complete. And that is the end of my lecture for today. And I wish you well. Thank you, and God bless, and bye for now.